Solve problems on trigonometric limits. This video is about the use of the formula limit as x approaches 0, sine of x divided by x is 1. Overview of problems. First problem, we compute limit as x approaches 0 of sine of x. Second problem, limit as x approaches a general number a, sine of x. Third, limit as x approaches 0, cosine 2 times x minus 1, and that divided by sine of x. Fourth, limit as x approaches 0 of cosine x minus 1 divided by x squared. Fifth, limit as x approaches 0 of sine evaluated at cosine of x minus 1 and that divided by x squared. Sixth, limit as x approaches 0, sine of x squared divided by x times sine of x. 7. Limit as x approaches 0, cosine of x minus 1 divided by x. 8. Limit as x approaches 0 of the quantity 5x minus sine of x, and that difference divided by 2 times x plus 4 times sine 3x. In problem 9, we compute the limit as x approaches 0 of cosine of 3 times x minus cosine 5 times x, and that divided by x squared. Number 10, limit as x approaches 0, 1 minus 2 times cosine of x plus cosine of 2x, and that sum divided by x squared. 11, limit as x approaches pi over 4, 1 minus tangent of x, and that divided by sine of x minus cosine of x. Problem number 12, limit as x approaches 0, square root 1 plus tangent of x minus square root 1 plus sine x divided by x cubed. And problem number 13, limit as x approaches 0 of the quantity x plus 2 times sine of x, and that sum divided by square root of x squared plus 2 times sine of x plus 1 minus square root of sine squared of x minus x plus 1. Next, I present solutions to these problems. You might want to stop the video now and try to solve these problems yourself. And then if you cannot, you may consult these video solutions. These problems are about trigonometric expressions and their limits. To most of these problems, there are several solutions because there are several trigonometric identities that may be used. In what follows, I present the solutions that I like the best. The limit of sine of x as x approaches 0 can be computed by resorting to the properties of the sine function. So the solution starts by recalling first how sine and cosine were defined. We look at the coordinate plane where the horizontal axis is now called the t-axis. And we place an angle of size x radians in this plane so that the vertex is at the origin and the starting side is the positive t-axis. The ending side is then the red half line emanating from the origin, and cosine of x and sine of x are the x and y coordinates of the blue dot indicated on this circle. So sine of x is the length of this dotted line segment, and x is the size of this angle in radians. So x is the length of the green arc on the unit circle. From this it follows immediately that if x is positive, then sine of x is less than x. If x is 0, then sine of x is also 0, then we have equality. So we have sine of x is at most x for x greater than or equal to 0. Now we use this fact that was immediate consequence of the definition, and we observe that since sine of x is at most x for x greater than or equal to 0, and since sine is an odd function, sine at negative of x is negative of sine of x, we get that negative of the absolute value of x is at most sine of x is at most the absolute value of x. This is a little bit delicate conclusion. The mistake that many people make at this point is that they write down negative of x is at most sine of x is at most x. This is of course not true. Now, the absolute value of x and negative of the absolute value of x, they both have the limit 0 as x approaches 0. Therefore, by the squeeze theorem, we get that limit of sine of x as x approaches 0 is also 0. To compute the limit as x approaches a general number a of sine of x, we have to start by first considering the cosine function. We have to figure out what is the limit of cosine as x approaches 0, and we first recall that by problem 1, limit of sine of x as x approaches 0 is 0. By trigonometry, cosine of x is 1 minus 2 times sine squared of x over 2. Therefore, by the properties of limits, limit as x approaches 0 of cosine of x is now limit as x approaches 0 of 1 minus 2 times sine squared of x over 2, and this is 1 minus 2 times limit as x approaches 0 of sine squared of x over 2, and again using properties of limits, this is the same as 1 minus 2 times limit as x approaches 0 of sine of x over 2, and that limit squared. Now as x approaches 0, also x over 2 approaches 0, therefore this limit as x approaches 0 of sine of x over 2 is 0, and we conclude that the limit of cosine of x as x approaches 0 is 1. We need this information just in a moment. By trigonometry, sine of x, which is of course sine of x minus a plus a, is sine of x minus a times cosine of a plus cosine of x minus a times sine of a. A is here now a fixed number. Hence, when we compute a limit of sine of x as x approaches a, it is the same as limit of sine at x minus a times cosine of a plus the limit of cosine of x minus a times sine of a, as x approaches now a. And now by the properties of limits, this is the same as cosine at a times limit as x approaches a of sine x minus a plus sine a times limit as x approaches a of cosine of x minus a. We already know by problem 1 that this first limit as x approaches a of sine of x minus a is 0, because as x approaches a, x minus a approaches 0. We also know that this second limit as x approaches a of cosine of x minus a is 1. Therefore, we conclude that the limit of sine of x as x approaches a is sine at a. To compute the limit of cosine of 2 times x minus 1 divided by sine of x as x approaches 0, we need to use a trigonometric formula. We use the double angle formula for cosine, and we get that cosine 2 times x minus 1, the numerator, is minus 2 times sine squared of x. Therefore, cosine 2 times x minus 1 divided by sine of x is minus 2 times sine squared of x divided by sine of x, which simplifies to minus 2 times sine of x, and we conclude that the limit as x approaches 0 of cosine of 2 times x minus 1 divided by sine of x is the same as minus 2 times the limit of sine as x approaches 0, but this limit is 0, hence the answer is 0. There are several ways to compute the limit as x approaches 0 of cosine of x minus 1 divided by x squared. Here I use the one I like the best. So I first perform the rewriting. Cosine of x minus 1 divided by x squared is cosine of x minus 1 divided by x squared, so the same expression itself, times cosine of x plus 1 divided by cosine of x plus 1. Of course, cosine of x plus 1 divided by cosine of x plus 1 is just 1, so this doesn't seem very intelligent for the moment. But cosine of x minus 1 times cosine of x plus 1, which we have now in the numerator, is just cosine squared of x minus 1, and that now has to be divided by x squared times cosine of x plus 1. And cosine squared of x minus 1 is minus sine squared of x. We use the property that sine squared plus cosine squared is 1. From that we get that cosine squared of x minus 1 is minus sine squared of x. So this becomes minus sine squared of x divided by x squared times 1 divided by cosine of x plus 1. But now this sine squared of x divided by x squared is of course sine of x divided by x, and that's squared. So we have now minus sine of x divided by x, and that's squared, times 1 divided by cosine of x plus 1. Sine of x divided by x approaches 1 as x approaches 0. Cosine of x approaches 1 as well. Therefore, we conclude that the limit of cosine of x minus 1 divided by x squared as x approaches 0 is minus 1/2. To compute the limit of sine at cosine of x minus 1 divided by x squared as x approaches 0, we first perform a rewriting. We observe that sine at cosine of x minus 1 divided by x squared is also cosine of x minus 1 divided by x squared times sine at cosine of x minus 1 divided by cosine of x minus 1. Now, of course, from the right hand side, cosine of x minus 1 would simply cancel out if we let that to do it. And then we would get back to the original expression. But we want to consider the right hand side expression rather than the original expression, because we already know what the limit of cosine of x minus 1 divided by x squared is. That limit is, by a previous problem, minus 1/2. So that part of this has already been dealt with. Next we observe that as x approaches 0, cosine of x approaches 1. This we also know by a previous problem. Therefore, cosine of x minus 1 approaches 0. And this means that we have limit as x approaches 0 of sine at cosine of x minus 1 divided by cosine of x minus 1 is just 1. And this means that the limit of the original expression, that is sine evaluated at cosine of x minus 1 divided by x squared, is now minus 1/2 times 1, which is minus 1/2. To compute the limit as x approaches 0 of sine of x squared divided by x times sine of x, we perform first a rewriting. We observe that sine at x squared divided by x times sine of x is the same as sine at x squared, and that divided by x squared times x divided by sine of x. Then we use the fact that the limit as x approaches 0 of sine of x is just 1, so we get that the limit as x approaches 0 of sine of x squared divided by x times sine of x is the same as limit as x approaches 0 of sine of x squared divided by x squared times x divided by sine of x. And both of these expressions in the product approach 1, therefore the whole limit is 1. To compute the limit as x approaches 0 of cosine of x minus 1 divided by x, we could use the result of a previous problem and compute and find out that this limit is actually 0. But in the solution, let us compute this limit without resorting to the results of a previous problem. We perform the rewriting. Cosine of x minus 1 divided by x is cosine of x minus 1 divided by x times cosine of x plus 1 divided by cosine of x plus 1. And now in the numerator we have cosine of x minus 1 times cosine of x plus 1, which is just cosine squared of x minus 1. So we get that cosine of x minus 1 divided by x is cosine squared of x minus 1 divided by x times cosine of x plus 1. But cosine squared of x minus 1 is minus sine squared, so this is the same as minus sine squared of x, and that divided by x times cosine of x plus 1. And this can be regrouped. It is minus sine of x divided by x times sine of x divided by cosine of x plus 1. And this first expression approaches 1 as x approaches 0. Cosine of x plus 1 approaches 2 as x approaches 0. And sine of x approaches 0 as x approaches 0. Therefore, we conclude that this limit is minus 1 times 0 divided by 2, which is 0. To compute the limit as x approaches 0 of 5x minus sine of x and that difference divided by 2x plus 4 times sine 3x, we have to do lots of technical rewriting. We want to use the fact which we know that sine of x divided by x approaches 1 as x approaches 0. So we rewrite in the following way. We first take the expression 5x minus sine x divided by 2 times x plus 4 times sine 3 times x, and we force x out as a common factor both in the numerator and in the denominator. So the numerator becomes x times 5 minus sine of x divided by x, and the denominator becomes 2x times 1 plus 2 times sine 3x divided by x. This looks already promising because x cancels out in the first place, and in the numerator we have sine of x divided by x, and in the denominator we have then 1 plus 2 times sine 3x divided by x. And this is almost in the form from which we can read the answer immediately. We get that the original expression is now the same as 5 minus sine of x divided by x, and that difference divided by 2 times 1 plus 2 times 3 times sine 3x divided by 3x. We added an extra term 3 and we multiplied and divided by it. Then we get sine 3 of x divided by 3 of x in the denominator. And as x approaches 0, this approaches 1. So we can conclude from this rewriting that the limit as x approaches 0 of 5x minus sine of x divided by 2x plus 4 times sine 3 of x is 5 minus 1 divided by 2 times 1 plus 6, which is 2 over 7. To compute the limit as x approaches 0 of cosine 3x minus cosine 5x divided by x squared, we have to use the addition formula for the cosine function to simplify the expression in the numerator. We observe that by trigonometry, cosine 3 times x is of course same as cosine 4 times x minus x, which is cosine 4x times cosine x plus sine 4x times sine x. This is the first term in the numerator. The second term is minus cosine 5x. Cosine 5x is cosine 4x plus x, which is cosine 4x times cosine x minus sine 4x times sine x. This is by the addition formula for the cosine function. Now in the numerator we had cosine 3x minus cosine 5x. So we have to subtract the expressions just obtained for cosine 3x and cosine 5x, and we observe that cosine 4x times cosine x cancels out, and we are left with 2 times sine 4x times sine x. So we conclude that cosine 3x minus cosine 5x divided by x squared is 2 times sine 4x times sine x divided by x squared. And this can be regrouped. It is the same as 2 times 4 times sine of x divided by x times sine 4x divided by 4x. The additional factor 4 appeared here because we wanted to arrange and rewrite so that the denominator of sine of 4x becomes also 4x. And now we can use the fact that sine of x approaches 1 as x approaches 0, then also sine of 4x divided by 4x approaches 1, and the limit of this whole expression is 2 times 4, which is 8. So the answer is that limit as x approaches 0 of cosine 3x minus cosine 5x divided by x squared is 8. To compute the limit as x approaches 0 of 1 minus 2 times cosine x plus cosine 2x divided by x squared, we first use the double angle formula for cosine. We get by trigonometry that cosine 2x is 2 times cosine squared of x minus 1. We substitute that in place of cosine 2x, and we get that 1 minus 2 times cosine of x plus cosine 2x divided by x squared is 2 times cosine squared of x minus 2 times cosine of x divided by x squared. And this can be rewritten as 2 times cosine of x times cosine of x minus 1 divided by x squared. And then we remember that we already know that cosine of x minus 1 divided by x squared approaches minus 1/2 as x approaches 0. This was a result of a previous problem. Therefore, the limit of this whole expression is 2 times 1 times negative 1/2, which is just minus 1. So the answer is limit as x approaches 0 of 1 minus 2 times cosine of x plus cosine of 2x divided by x squared is minus 1. We have to compute the limit as x approaches pi over 4 of 1 minus tangent of x divided by sine of x minus cosine of x. As x is pi over 4, sine of x and cosine of x take the same value, therefore the denominator takes the value 0. Also tangent takes the value 1, therefore also the numerator takes the value 0, which means that we cannot compute this limit by direct substitution. So we have to work with this expression for which the limit has to be computed, and we first substitute in place of tangent sine divided by cosine. So we get 1 minus tangent of x divided by sine of x minus cosine of x is 1 minus sine of x divided by cosine of x, and that whole expression divided by sine of x minus cosine of x. This simplifies to cosine of x minus sine of x divided by cosine of x times sine of x minus cosine of x. So now we have in the numerator cosine of x minus sine of x, and the factor in the denominator is sine of x minus cosine of x. So these two things cancel out, and they result to just minus 1. So we conclude that the whole expression is minus 1 divided by cosine of x. And now the limit is easy to compute, because we know that cosine of x as x approaches pi over 4 approaches cosine at pi over 4. This was a result of a previous problem that implies this. And this means that the limit of this whole expression as x approaches pi over 4 is minus square root of 2. To compute the limit as x approaches 0 of square root of 1 plus tangent of x minus square root of 1 plus sine of x divided by x cubed, we have to get first rid of the difference of the square roots in the numerator. So we do a rewriting. We take the original expression and we multiply and divide it by the sum of the two square roots appearing in the numerator. So the original expression becomes square root of 1 plus tangent of x minus square root of 1 plus sine of x divided by x cubed, that was what we had, times square root of 1 plus tangent of x plus square root of 1 plus sine of x, and that divided by the same expression. Now this whole thing got rather long, but simplification happens, because in the numerator we have the difference of square roots times the sum of the square roots. And the product is simply 1 plus tangent of x minus the sum 1 plus sine of x. 1 cancels out. We have tangent of x minus sine of x divided by x cubed times square root of 1 plus tangent of x plus square root of 1 plus sine x. Tangent of x is sine of x divided by cosine of x. So we have that the original expression for which the limit has to be computed is sine of x divided by cosine of x minus sine of x, and that difference divided by x cubed times square root of 1 plus tangent of x plus square root of 1 plus sine x. So this is our rewriting. We already have observed that the original expression is sine of x divided by cosine of x minus sine of x, and that divided by x cubed times the sum of the square roots. Now these terms can be rearranged. We have sine of x divided by x here times 1 minus cosine of x divided by x squared times 1 divided by cosine of x times the sum of the two square roots. And in this form the expression is manageable, because we know that sine of x divided by x approaches 1 as x approaches 0. We also know that 1 minus cosine of x divided by x squared approaches 1/2 as x approaches 0. Then we are left with 1 divided by cosine of x times the sum of the square roots, but that can easily be dealt with. So we conclude that the limit as x approaches 0 is 1 times 1/2 times 1/2, which is 1/4. In this problem, we have to compute the limit as x approaches 0 of x plus 2 times sine of x divided by square root of x squared plus 2 times sine x plus 1 minus square root sine squared of x minus x plus 1. Here, a direct substitution would result to 0 divided by 0, which is not a number. So direct substitution does not work. We have to perform a rewriting. And we have a problem that we have to deal with first, which is the difference of the square roots in the denominator. We get rid of that difference by a standard rewriting. We multiply and divide by the conjugate expression. So we take the original expression x plus 2 times sine x divided by square root of x squared plus 2 times sine x plus 1 minus square root of sine squared minus x plus 1. And we take the sum of these two square roots. We multiply and divide by it. So the whole expression now becomes x plus 2 times sine x divided by the difference of the square roots times the sum of the square roots divided by the sum of the square roots. Now this expression would be very long if we were to write it completely, but we now use the abbreviation. The first square root appearing in the denominator is square root of x squared plus 2 times sine of x plus 1, and the second square root is square root sine squared minus x plus 1. Now in the denominator we have the difference of square roots times the sum of the square roots. This product is simply the first square root squared minus the second square root squared. And when we perform this computation, we get that the original expression is now x plus 2 times sine of x divided by x squared minus sine squared of x plus 2 times sine of x plus x times the sum of the two square roots. Next, we rewrite this so that we divide every term by sine of x. So we get that the original expression is x divided by sine of x plus 2, and that divided by x squared divided by sine of x, but x squared divided by sine of x is x times x divided by sine of x. Then we had minus sine squared of x divided by sine of x, which is just minus sine of x, plus 2 plus x divided by sine of x times the sum of the square roots. Now, from this form, we can see that what the limit is, because x divided by sine of x approaches 1 as x approaches 0. And we get that the limit is 1 plus 2 divided by 0 times 1 minus 0 plus 2 plus 1, and that times 2. This 2 is the limit of the sum of the two square roots, and the whole expression simplifies to 2.